Hello, and thank you for tuning in. My name is Chris Lillard, and this is checkpoint number 3 for our final project. The course is ECE5505, Design Verification Testing, and my topic is Test Architectures for Stacked Integrated Circuits. We'll get through this quickly because we don't have a ton of time. I did have a little bit of background information that'll help make the rest of this a little bit more interesting and useful to the group. So, brief history of stacked ICs. You saw TSVs coming to the stage with William Shockley, who was also famously on the research group that put forth the patent for the transistor from Bell Labs. TSV stands for through silicon vias, and that is the interconnection strategy to get from a substrate or an interposer board onto an IC or a die, or even to puncture through a die into an additional layer, so enabling three-dimensional stacking. By the late 1980s, you saw other research groups aside from Bell take on work to develop stacked IC topologies. This was done in the early 1990s in the form of wire bonding, and then by 1995, you saw them actually taking the chip, flipping it over, and allowing ball grid arrays to be used as the interconnect from substrate to chip. And then we'll skip ahead to 2010. You see through silicon via entering the industrial mainstream, so it becomes very lucrative for these companies to be able to take on, based on like the research and development, the cost being driven down from the side of adoption. The technology that was enabled based on these TSVs for multi-layer stacking has made it a very lucrative technology, as you'll see from some of these examples here in the next couple of slides. So some of the benefits, we'll skip through this just for the sake of time. This is used heavily in the fields of field programmable gate arrays, FPGAs, as well as HBMs. And today you're seeing a lot of development done in the realm of AI ML accelerators, which also relies on HBM technology as well. So rife with multi-layer stacking. So to get to our papers of interest for this checkpoint, the first one that I wanted to talk to was the use of microbumps between in TSVs for interconnections between die packages and substrate boards. The group that put this out is actually very involved with standardizations for automatic test pattern generations for things like UCIe and others. And so what they've done is actually gone through and assigned a neighborhood size. So they're asking the designer to go through and determine in the lower left figure here the value for rho, which is a floating point value that dictates, the kind of the region of influence from this target victim node or bump to all of the aggressor candidates. And so that's kind of used to pare down the scope of the automatic test pattern generator and improve the amount of time that it takes to do the test design and verification. The other one that I wanted to talk to is this built-in self-test solution. This is really an interesting topic, and I thought that it was especially relevant for our class. What they're doing is actually asking the designers to take additional space to incorporate spare through silicon via interconnections from die to die. And what that allows is if you have a failure point at a specific TSV, then you can see in the bottom right figure here, they're actually rerouting multiple interconnections so that the spare can be utilized. And what is really interesting about this is that you have all of these die that have already gone through their own design verification, right? So what you see is these are like known good die that will be interconnected in a multi-layer strategy and will then fail. And so oftentimes that just decreases your yield. You have to throw the board out. And for what? Because your interconnection from die to die was the failure point. So this is a very important method for recouping some of those lost multi-layer systems that are comprised of working chips and non-functional interconnections. Thank you so much for listening.